Okay, hello. Good evening, everyone. My name is Avik Mukhopadhyay, and I'm a PhD research scholar at the Department of Electrical Engineering at IIT Madras. And I welcome you to the uh, ninth live session for Signals and Systems. So far, we have explored a lot of theory on the topics, variety of topics, and in the last week, till the last week, we were primarily focusing on the Laplace transform, region of convergence, and uh, the system properties, right? So now, in the ninth week of the course, we were introduced to the notion of Fourier series, right? So this is a scenario where we are computing Fourier transform of periodic signals, which results in Fourier series coefficients. Okay, so we looked at the exponential representation of Fourier transform and for periodic signals, how do we calculate those Fourier series coefficients, and what are the different properties of those Fourier series, right? So what happens if we transform our signal? What happens to our Fourier series coefficients? So we'll look at some examples and also look at the various properties of Fourier series coefficients in this session. So let's get started. So we have the first question on the screen, in which waveform is given for a periodic signal x of t, and it has a rectangular wave pattern, as you can see, and that it has a triangular wave pattern, and it is periodic, so it repeats throughout the entire range of time, and we are asked to determine the continuous time Fourier series coefficients, the CTFS coefficients of this signal in the exponential form. So if you remember, we have looked at the exponential series representation of Fourier transform using so it's basically representing a periodic signal as a linear combination of phasors, if you recall. So we represented any x of t, which is a periodic signal, as summation k running from minus infinity to infinity ak times e power jk omega naught t, where ak are your Fourier series coefficients, and this e power jk omega naught t are the phasor terms, which are periodic, right? So that's why you are able to represent any periodic signal, of course provided that it satisfies the Dirichlet conditions, and then only you'll be able to take its Fourier transform, and so yeah, so the information about the signal x of t is captured inside these Fourier series coefficients, these AKs, okay, and they are your continuous time Fourier series coefficients, these AKs. So that's the representation, and we can also find these AKs using a formula. So basically a naught, which is the coefficient for index 0, k equals to 0, a naught is obtained simply by taking the average value of x of t over one period, okay, and you can obtain the general expression for ak for k not equals to 0 using another formula. So I'll revisit all of them. We'll need all those things in this numerical. So let's start. Okay. First, let me draw the given signal. it is a periodic signal. Let's say this is the time axis and this is your signal x of t, and let's say this is the point t equals to 0, and you have a repeating pattern of triangular waves. So it has this kind of an appearance. This height, the height of every triangle is a units. If you go back to the question, its height is a. This. So, and every triangle is 1 unit wide in time axis. Okay. So 0 to 1 we have a triangle, then we have 1 to 2, then we have 2 to 3, and so on. It repeats. Similarly, in the negative direction, negative time also we have the same pattern. And so on. So it is clearly a periodic signal, and what will be the fundamental period of this signal? It is clearly visible that the fundamental period of this signal is capital T equals to 1, because you see this pattern repeats after every 1 unit of time. Okay, and that's the smallest possible time period. Okay, so capital T, the fundamental period is 1, and we know that the exponential Fourier series representation of a periodic signal x of t has this form: summation k running from minus infinity to infinity ak e power j k omega naught t, where omega naught is your fundamental frequency. Okay, so capital T is the fundamental period, fundamental time period, or simply fundamental period, and omega naught is your fundamental frequency. And how are these two quantities related? Omega naught is basically equal to 2 pi by capital T. This is the relation. We know this. So in this case capital T is 1, and omega naught can also be obtained from capital T. So omega naught is 2 pi by capital T, and capital T is 1 here, so omega naught is 2 pi. Okay, so if let's say the time is in seconds, so the period is 1 second, and omega naught would be 2 pi radians per second. Okay, that would be the unit. Okay, so now the task is to find the continuous time Fourier series coefficients. That's what has been asked in the question. So we usually take two cases. One for k equals to 0, we compute a naught by simply, as I said, finding the average value over one period. And for the other case, for k not equals to 0, the general form of ak for k not equals to 0. So how do we get a naught? It is simply obtained by taking the average value like this over one period. So you integrate x of t with respect to dt over one time period. Okay, and so you have to scale the entire thing by the time period. So 1 by capital T comes here. So this notation, so I have used this integration symbol, and I have written capital T in the lower limit side. So this actually is a representation of the fact that you are integrating over one time period. So this in general, this notation, okay, this in general could mean an integration over an upper limit and lower limit chosen such that the difference between the upper limit and the lower limit is equal to your fundamental period capital T. Okay, so this could be any integral from t1 to t2 such that the difference between the limits is capital T. Okay, so you can either integrate from 0 to capital T, or from minus capital T by 2 to plus capital T by 2, and so on. Okay, as long as the difference is capital T, you're fine. Okay, so for simplicity, let me actually take the limits from 0 to capital T. So a naught is 1 by capital T, 0 to capital T, x of t dt. Okay, and we already know that capital T in our signal is actually 1. So t becomes 1. So this is nothing but 0 to 1 x of t dt, since t is 1. So now what? So the limits of integration are 0 to 1, and within this limit our function x of t is linearly increasing, as you can see. And what is the slope? The slope is basically capital A, because you are traversing one unit along the horizontal axis, whereas you are traversing capital A units along the vertical axis. So your slope would be capital A. So the equation of x of t within this region 0 to 1 is nothing but x of t given by capital A into t, right? So capital A, with capital A slope, it is increasing, okay, as a function of time. So you can replace x of t by a times t in this limit. So if you evaluate this integral, so basically the integral of t dt will be t square by 2. So there will be a factor of half. We already have a factor of capital A, which is a constant independent of t. So those two factors, a by 2, will come outside, and we'll have t squared, and we have to take the limits. So this will give us a by 2 into 1 minus 0. So this is a by 2. Okay. And in case of time constrained situation, when you have to compute this very quickly, let's say without doing all these steps, computation of a naught, the uh, Fourier series coefficient corresponding to index k equals to 0, is the simplest one. What you can do is you can simply consider this triangle. I mean, in this case the shape is triangular, need not be triangle. So this shaded region is the shape of the signal in one fundamental period, right? In this case from t equals to 0 to t equals to 1. So basically what you are doing to find A naught is finding the area of this shaded region within one period and dividing that area by the fundamental period. So what is the area of this shaded region, this triangle? This is half into base into height. So in this case, the base is 1 and height is A. So half into 1 into A is A by 2 units. Okay, so that's the area. And you are also dividing that by capital T because you have to take the average over one time period. So on dividing that by capital T being equal to 1 here, so it makes no change. So the final answer is A by 2. So that way also you can verify that, okay, the expression that you got for A naught is actually correct, right? Okay. So A naught is A by 2, capital A by 2. Now for K not equals to 0, what is my AK? For K not equals to 0, the expression for AK has a slightly different form. So you'll have that scaling factor of 1 by T here as well, and you are integrating again over one time period. You have x of t inside the integral. Now the only additional thing is you will have another multiplicative factor of e power minus j k omega naught t, okay, dt. So you have to evaluate this integral to find the other Fourier series coefficients which are corresponding to indices other than k equals to 0. So let us do that, and again let's say I'm choosing the limits from 0 to capital T. So you can choose any limit such that their difference is equal to capital T. So 0 to capital T x of t for minus jk omega naught t dt. So let me see if my connection is smooth. It's fine. Yeah. Okay. All right. So yeah. And now what can we do here? So we can simplify this also because we know already what is capital T. It is equal to 1. So I know my limits also, and within 0 to 1 interval I saw that x of t had the form a times t, right? We saw that while calculating a naught. Okay, so x of t gets replaced by a t times e power minus j k omega naught t. So what about omega naught? Omega naught I had already figured out, it is equal to 2 pi using the relation between omega naught and t, right? It is omega naught is given by 2 pi by capital T. Capital T is 1, so omega naught is 2 pi. So this, I can substitute omega naught here. This. Since t is equals to 1 and omega naught equals to 2 pi. Now this factor capital A is a constant which is independent of t, so it comes out of the integral and we are left with t times e power minus j 2 pi kt dt. Alright, so now how do we evaluate this integral? Well, we are familiar with this kind of integrals involving product of two functions of the variable. So here we have product of two terms, right, which are individually functions of t, which is the variable of integration. The first function is simply t and the other function is e power minus jk minus j 2 pi kt, right? So we have an algebraic function and we have an exponential function. Okay, the product of these two functions inside the integral, and we have seen this in our high school mathematics that to solve for these kind of integrals we need to use integration by parts, and it has a particular formula, and the rule that we use to evaluate this integral, uh, it has a code which is given by eyelet, right? So you decide how to evaluate this function by assigning priority to the function. So one of the functions is labeled as the first function and the other one is chosen as the second function based on that eyelet rule. Okay, so what is that eyelet rule, if you recall? So first of all, this has to be solved using integration by parts. And what is the eyelet rule that I am talking about? So okay, so I stands for inverse, L stands for logarithmic, A stands for algebraic, T stands for trigonometric, and finally E is the acronym for exponential functions. Okay, so the function that falls to the right side within this sequence, as you move from left to right, you are moving from I, L all the way till E, right? So the function which among the two functions which falls to the left category will be your first function, and the one which falls to the uh, right category will be chosen as the second function. For example, in this case, there is a product of two terms, t and e power something. So that t is an algebraic function. So we have this algebraic function, and then we have an exponential function. So that falls in the category of capital E, right? Now, since exponential is the one with the, uh, it is at the extreme right, so it will always be the second function, and the, the function t belongs to the class A algebraic, which is to the left of E, so it is chosen as the first function. Okay, so and there is a rule also. Okay, so suppose you have uv, integral uv, and if u is your first function, someone wants to join, I think. Okay, so hello Shrikant, can you hear me? Yeah, you can unmute and respond if my audio is clear, if you're able to see the screen. Hello. Okay, so this is the first function and this is the second function. And to evaluate this, once we have decided what is our first function and what is our second function, then we can evaluate this integral. So v dx, let's say both are functions of x. Okay, so the uh, variable of integration is x. So this minus integral du dx, you differentiate the first function, then you integrate the second function, and then you again integrate the whole thing. So this is the function actually. Okay. So this is the rule of integration by parts. So in this case, the first function is your t, because it is on the left side of the priority rule. So this is chosen as your first function, and the exponential function, of course, it is the highest priority, so it's the second function. And now we can use this rule to solve the integral. Okay, so let us first solve the integration t e power minus j 2 pi kt dt. Then once we have the form, then we can simply substitute the upper and lower limits and calculate. And we also have a scaling factor of a, so that's nothing to worry about. So what I will do is I will first use integration by parts to calculate this integral. Okay, so this is my first function, and this is my second function. So I have t coming out, and then this minus integration d dt of t times integral e power minus j 2 pi kt dt, this whole thing dt. Now this first term becomes e power minus j 2 pi kt divided by minus j 2 pi k minus integral. So the differentiation of t with respect to t is 1. So this term becomes 1, and once we integrate this exponential term here, we'll end up with e power minus j 2 pi kt divided by minus j 2 pi k, and again we have this dt here. Okay, so what do we have? So t by minus 2 j pi k e power minus j 2 pi k t. So there are two minus terms here, so it becomes plus, and I can pull this 2 pi jk outside the integral. Then I have e power minus j 2 pi kt dt. Okay, okay, and now what do we have here? Minus j 2 pi k. Okay, is t by 2 pi jk e power minus j 2 pi kt plus e power minus j 2 pi kt whole divided by 4 pi square k square. Because what happens here is I have this product of two terms in the denominator for the second term. So I have 2 pi k whole squared, which gives me 4 pi square k squared, and I have j times minus j. So I know j is the square root of minus 1, so j square is minus 1, and now here I have minus j square, so that gives me 1. So I have overall 4 pi square k square into 1, which is same as 4 pi square k square. And okay, so yeah, so that's the integral. Yeah, this is the integral. You can take common also, but I think this form is fine. All right, now this is the form for our integral in hand. So I can just change the ordering, so keeping the term with the positive sign in front and just doing this small thing, 2 pi jk to e power minus j 2 pi kt. So now what we will do is we'll substitute the upper and lower limits. Okay, so basically we'll have a factor of a outside as well and take the limits. So now my ak, again, for this is for the case for k not equals to 0, is a times 0 to 1. This was the term, right? And we just found this integral. So this is the expression, and we'll substitute the limits now. Okay, so what do we get? A times upper limit is 1, so if we plug in 1, what happens? So the first term becomes e power minus j 2 pi k, t is 1, then we have 4 pi square k square. Okay, then for the second term we have, again we are putting t equals to 1, so e power minus j 2 pi k divided by 2 pi jk. Fine, so this is my first term. Now, I mean, the term which results from the substitution of the upper limit. Now, for substituting the lower limit, which is 0, what do we get? So e power minus j 2 pi k into 0, so that gives me 1. Okay, minus, again this term will be simply 0 because I have t as a multiplicative factor. Okay. Now, um, so what about this term here? E power minus j 2 pi k. So e power minus j 2 pi k is actually 1. Why? Because, so you can write e power minus j 2 pi k as cos minus 2 pi k plus j times sine of minus 2 pi k using the Euler's formula, right? So this now can also be written as cos 2 pi k, because cos minus theta is same as cos theta, and you can bring this negative sign from the argument of sine outside. You have sine 2 pi k, because sine minus theta is minus of sine theta. Sine is an odd function, right, and cos is an even function, so that's why it's happening. Now k here is an integer, right? So k is an integer here. because it's an index, it's an integer. Okay, it can take only integer values. So k is actually an integer. K belongs to z, integer. So these Fourier series coefficients are defined for integer indices. Okay, so now so what happens to cos of 2 pi k? So this is basically cos of any multiple of 2 pi, so that will always give you 1. And what about sine 2 pi k? That will always give you, so that's a sine of multiple of 2 pi, so that will always give you 0. So that is 1 minus 0, so that's simply 1, right? So now if I go to the next page, this function, therefore ak equals to, again for k not equals to 0, continuing our calculation, there was a outside, and this term here, this becomes 1, e power minus j 2 pi k. So this becomes 1, 4 pi square k square minus, again similarly this term e power minus j 2 pi k, this also becomes 1, and on the denominator I had 2 pi jk, and the next term was 1 by 4 pi square k square. So these two gets cancelled, and I have a by 2 pi jk, and you can also, sorry, a by, so there will be a minus sign as well, yeah, minus a by 2 pi jk, which you can also write it as a times j divided by 2 pi k, because I have minus 1 by j, so that gives me j, right? Because j square is minus 1, right? So now we have found the Fourier series coefficients. We have complete knowledge of the Fourier series coefficients, and that captures the information about your signal also. So what I have here is, I already found a naught corresponding to k equals to 0, right, at the very beginning. So a naught was capital A by 2, the average value over one time period, if you remember. So that is for the case of k equals to 0, and for non-zero k, I found that ak has this form given by capital A times j divided by 2 pi k for k not equals to 0. So these AKs are my continuous time Fourier series coefficients, or CTFS. Okay. Now you can also explore some uh, you know, these coefficients graphically. Typically, when we have these kind of complex entities, we can analyze them in two ways. Mostly, one is their magnitude spectrum, and the other is looking at their phase response. So basically, that's how you analyze a complex number, right? It has a magnitude component and a phase component. So you can check for that as well, for these Fourier series coefficients. But yeah, so this is how we compute the Fourier series coefficients. Okay, right. Now moving to the second one. Okay, fine, right. Now for the second question, it is mentioned that we have a 2 pi periodic signal x of t. So this signal x of t has a time period of 2 pi, and x of t is specified over one period, that is uh, from 0 to 2 pi, as you can see. So x of t has three different forms within these sub intervals, right? From 0 to capital A, it has the form t by capital A. From capital A to pi, it has the value 1. From pi to 2 pi, it has the value 0. Okay, so the entire time period 0 to 2 pi has been split into three sub intervals, in which this function x of t is having three different forms. Okay, now you have to represent this x of t in its exponential Fourier series. Again, we have seen the exponential Fourier series representation as that linear combination of phases, remember? So for that we need the knowledge of the Fourier series coefficients, right? The AKs. So first thing is to find those AKs. Okay, we know the time period is 2 pi, so that automatically tells you the fundamental time period, and that automatically tells you the fundamental frequency omega naught. And then you can use the formula to find the coefficients, Fourier series coefficients. Once you have the coefficients, you simply just express x of t in the exponential Fourier series representation. So let's do that, but first let us visualize this graphically. Okay, so we're in the second question, and we already know that the fundamental period is 2 pi. Okay, fundamental period, because it is given in the question that it is 2 pi periodic, and within one fundamental period, that is from 0 to 2 pi, the form of the function has been given. Okay, so let me here itself calculate omega naught as well, obtained by 2 pi by capital T, which is 1 in our case because t is 2 pi. So it is given that x of t has this form t by capital A for 0 to capital A interval. Okay, so this is less than A, and it has value 1, this, and 0 from pi to 2 pi. Yeah, so let us try to look at its graph. Okay, so x of t is my function, and so this is the time axis. So from 0 to 2 pi, how does it look like? So let's say 0 is somewhere here. So that 0 to 2 pi is split into three parts. Okay, so first is 0 to capital A. Let's say capital A is somewhere here. Then capital A to 2 pi, sorry, capital A to pi, and then pi to 2 pi, like this. So from 0 to A, it has the form, x of t has the form t by capital A. So it is basically a straight line with slope 1 divided by A, Okay, 1 divided by capital A. So let's say something like this. Okay, so the slope of this line is 1 by capital A, and the form is basically telling you the slope. The form is t by capital A, so the slope is 1 by capital A. So at t equals to capital A, what is the value of x of t? Basically it is capital A by A, which is 1. Okay. And from this second interval also you can see that at t equals to capital A, it is, you know, equal to 1. So from capital A to pi interval, it stays at 1 like this, and from pi to 2 pi it falls to 0 and stays at 0 like this. And this pattern actually repeats. So the same thing will be repeated after every 2 pi interval. So from here, from this 2 pi, it will again start to, increase with a slope of 1 by a, then reach the value of 1. So this point will be 2 pi plus capital A. Then this point at which it falls back to 0 again will be at 3 pi, and from 3 pi to 4 pi it will stay at 0. So this point is 4 pi. Okay, and so on, it will just repeat. Okay, I'm just drawing one repeated pattern on either side of the time axis. So similarly on the negative side also we will have this pattern. Somewhere here I'll have minus pi, so this will be like, you know this yeah, this point is minus 2 pi plus a. You can check for these small things. It's not very tough to figure out. So and it goes to 0. So this point will be minus 2 pi. Okay, and from minus pi to 0 it will stay at 0. It's like this. So yeah, and it will repeat. So more or less it has this kind of a repeating pattern. So clearly this is a periodic signal with period 2 pi. Okay, now we need to find its exponential Fourier series representation, so which is given by x of t goes to summation k running from minus infinity to infinity a k e power j k omega naught t, right? And we already know omega naught, we have already calculated it here, so it's equal to 1. This will be summation k running from minus infinity to infinity ak e power j k t, because omega naught is 1. So first let me find a naught, which again you can simply find the area so over one period. So one time period is 0 to 2 pi. So this is your capital T, which is equals to 2 pi. Okay. So over this time period, you find the area and then you divide by the period. So what is the area over this interval 0 to 2 pi? See, you have a trapezoidal figure here. So what is the area of this trapezoid? So this figure, I'm talking about this trapezium. So its area is, so the area for trapezium is given by half into sum of parallel sides into distance between them. So this is half into sum of the parallel sides. These are the parallel sides. Okay. So the shorter parallel side is of distance is of length pi minus a, and the longer one is of length pi. So sum of them is equal to pi minus a plus pi, which is 2 pi minus a, and the distance between them is, the perpendicular distance is 1 units, so it's simply 1. Okay, so you have yeah, 2 pi minus a whole divided by 2 basically. And again remember, you have to divide this by the capital by the capital T, the fundamental period. So area divided by capital T will give you 2 pi minus a divided by, you already have a factor of 2 in the denominator, then you are further divided by capital T, which is 2 pi, so you'll have 4 pi. Okay, which is nothing but which is nothing but half minus a by 4 pi. Okay, so this is what you are supposed to get. So now let us see if our calculation also gives the same value or not. So a naught, by our formula we know that it is given by the average value of the signal over one time period, given by this. So again I am choosing the period from 0 to capital T. You can choose any t1 to t2 such that t2 minus t1 is equal to capital T. This, right, and what do I have here? Okay, now capital T is known to you, right? Capital T is 2 pi, so I can substitute that here like this. Capital T is 2 pi. Okay, now I have to identify the forms of x of t in those sub intervals, right? So I can split this whole integral into sum of three integrals. So one integral would be from 0 to capital A, and within this interval my function has the form small t by capital A. So small t by capital A dt plus the second sub interval would be from capital A to pi, capital A to pi, right? And in that interval the function is 1, plus actually it will be 0, because for the third sub interval from pi to 2 pi it is 0, so it won't contribute to our um, summation. Now it's simple, we can find this easily. So this first integral will evaluate to t square by 2 into capital A. So 1 by 2 into capital A can be pulled outside, and you have t squared with the limits 0 to capital A. And similarly, this one will give you pi minus capital A. Okay, and so this is 1 by 2 pi into 1 by 2a into a square minus 0. So this is a square plus pi minus a. This is 1 by 2 pi into a by 2 plus pi minus a. Okay, so which is nothing but 1 by 2 pi into pi minus a by 2, so which is again half minus a by 4 pi, which is exactly what we calculated before by simply taking the area and dividing by the fundamental period. Okay, this thing is the same form. Okay, so my a naught is half minus a by 4 pi, and now for k not equals to 0, what is my Fourier series coefficient? Ak. For this you have to take the other formula, which is this one, this jk omega naught t dt, and capital T is 2 pi, choosing the limits from 0 to 2 pi, x of t e power minus j k omega naught. Now what about omega naught? Omega naught is 1 in our case because t is 2 pi, omega naught is 1. We had already uh, calculated those things. So this is minus j k t dt. Okay, okay, so this is 1 by 2 pi. Now again I'll split this integral into 3 sub-integrals, right? So 0 to a would be the first sub-interval, and the same thing which I did for computation of a naught dt, plus then a to pi, right? From a to pi the value of the function is 1, so I'll have this, okay, inside integral. And of course the third part will not contribute because x of t in that interval, which is pi to 2 pi, x of t in that interval is simply 0. So now what do I have? 1 by a 0 to capital A integration of t into e power minus jk t dt, plus for this term we can calculate the integral, that's easy. So this will be the integral, and now we have to substitute the limits. Okay, so now this, for this function here, for this integral we again have to use integration by parts, as we did for the first question. So let me first calculate it. And again, you can very well tell that this is going to be your first function because it's an algebraic function. First function, and this is an exponential function, so it will be your second function. So now you can evaluate this as follows. Minus integral. So you'll have that derivative of t, which will be 1. I'm not writing it. This. Okay. So all you need to be while solving this, integral is just to be careful. That's it. And I don't think these kind of time-taking integrals will be there in the final exam, but it's just for practice. So this would give you t times e power minus jkt by minus jk. So there is two minus terms here, which will become plus minus jk by minus jk, and actually I think this kind of form, whenever you have biparts of this form, some t times e power some function of t, um, you can actually I think that if integral has some standard form, okay, uh, so if you memorize that, then it will solve, it will just save your time, right? You need not work out the derivation by doing all this isolate and all. Okay, so this will give you plus e power minus jkt divided by k square. Okay, k square. Okay, and again, let me just swap the order because I want to keep the positive term in front. Hmm. Now we can find our AK. Okay, so we were till this point. So now we have found this integral. Okay, the form for this integral. All we need to do is substitute the upper and lower limits. So from here, I will now substitute. So 1 by 2 pi. Why 1 by 2? Because we already had the scaling factor. And then I will have 1 by a, and this is the integral result. I write this, and the limits were 0 to capital A. And also there was another term. All we need to do for that is just substitute the limits. So the first upper limit is pi, So it will be e power minus jk pi divided by minus jk. So let's write it down. This is e power minus jk pi divided by minus jk minus e power minus jk into capital A divided by minus jk. Yes. So this is, now let us substitute the limits. So e power minus jk a, because my upper limit is a into e power minus jk a divided by jk, then I have 1 by k square, and this term will go away because the lower limit is 0. Fine. And so here I have two minus terms which will become plus, so I'm bringing that in front. E power minus jk capital A divided by jk, and this term I'm keeping on the rightmost end, so this is e power minus jk pi divided by jk. Okay, fine. So now we are almost done. I think there will be some terms which will get cancelled. So this is 1 by 2 pi, and let's take this 1 by capital A factor inside. So we will have e power minus jk capital A divided by a k squared minus, so this a and a will get cancelled, minus e power minus jk a divided by jk minus 1 by a k squared plus e power minus jka divided by jk minus e power minus jk pi divided by jk. Okay, so these two terms get cancelled, and what do we have? Okay, let us try to simplify this further if possible. So I can take this 1 by ak square terms together. Okay, so I'll take 1 by ak square common, and I'll have e power minus jka minus 1. This will be, so I'm clubbing these two terms together. Okay, and what I'll be left with is this term on the rightmost end, so which is e power minus jk pi divided by jk, and I can actually write e power minus jk pi as minus 1 to the power k. Why? Because see, e power minus jk pi is nothing but cos of minus k pi plus j sine minus k pi, again using Euler's identity. So you'll have cos of minus k pi is same as cos of k pi, because cos is an even function, and sine being an odd function, this minus sign will come out, minus sine k pi. Okay, and now this is simply 0 because sine of k pi, sine function evaluated all at all multiples of pi is simply 0. So we are left with cos k pi, and cos k pi is same as minus 1 to the power k. For all even values of k, even integral values of a, for of k, cos of k pi will be plus 1, whereas for all odd integer values of k, cos of k pi will be minus 1. So it will keep alternating between plus 1 and minus 1 depending on the nature of k, whether k is even or odd. Okay, so this is simply minus 1 to the power k. So this is minus 1 to the power k. Sorry, I think there will be a minus sign. Okay, minus 1 to the power k divided by jk. Okay, and yeah, so we have this term here. I'm just adjusting with a negative sign here, and so this in the second term we have 1 by jk in the denominator, and we have a negative sign in front. So if I have to bring this j in the numerator, I can do that, right? Basically I have minus 1 by j here, so that is nothing but plus j. So j will come in the numerator, so this will give me j into minus 1 to the power k divided by k. So 1 by 2 pi j into minus 1 to the power k divided by k minus 1 minus e power minus jka divided by ak square. Okay, so this is the form of my Fourier series coefficient for k not equals to 0. So how can I summarize the result? Okay, for k equals to 0, what did I get? A naught. I got a naught as half minus a by 4 pi, right? Half minus a by 4 pi, and we had verified this in both ways by just calculating the area simply and also through formula. And for generally k not equals to 0, I am having this form. For k not equals to 0. So you have the complete knowledge of your Fourier series coefficients, and the information about the signal x of t is captured within this Fourier series coefficient, and you can represent your x of t by using this Fourier series coefficients using the exponential Fourier series representation. Okay, so the second question is also done. Now moving to the third one. Okay, here we go. So alright, so in the third one we are given the Fourier series coefficients, so we know what the AKs are. Okay, so AK has the form J times K for mod of K less than 3. Okay, which means that mod of K less than 3 means K lying between minus 2 to plus 2 basically, because K is always an integer, so the set of integers which satisfy mod of K less than 3 would be minus 2, minus 1, 0, 1 and 2. Okay, so for these 5 indices, AK has the form J times K and it is 0 otherwise. Okay, so we just need to calculate these 5 coefficients to completely characterize our x of t signal. And on top of that we are given that x of t plus 4 is equals to x of t. So which straight away tells you that the fundamental period of this signal is 4, right? So because after 4 units of time, your signal is getting repeated. So what do you know? So you know the Fourier series coefficients. These AKs are known to you. You also know the time period. That's it. Now you can simply find the Fourier series representation, the exponential Fourier series representation for x of t. So let's do that. Okay. The third question. AK is given to you. Okay. It is J times K for mod of K less than 3 and it is 0 otherwise. So this tells me this is the same thing as AK same as JK is equal to JK for minus 2 less than or equals to K less than or equals to plus 2. Okay, and K is an integer here. Always remember that K is an index. So K is always an integer. So for this range of K, it is JK and it is 0 otherwise. So there are only 5 non-zero coefficients basically. Okay, we still don't know if it's going to be non-zero or not, but we are only concerned about 5 Fourier series coefficients. Okay, we need to calculate only those 5 because the rest of the coefficients are always 0. Okay, so now and yeah, and one more thing, x of t plus 4 is equals to x of t is given. So it's given, and this tells you that your fundamental period is going to be 4 fundamental period of your signal, of course, x of t. And from capital T you can also now find omega naught, okay, which is pi by 2. What is omega naught? Fundamental frequency. Fundamental frequency. Omega naught is pi by 2. Okay, now let us find the coefficients one by one. So for k equals to minus 2, k equals to minus 1, k equals to 0, k equals to 1 and k equals to 2. Let's calculate AKs. So a minus 2 is how much? For k equals to minus 2 I am finding AK, so it will be a minus 2. So and it has the form j times k. So j times minus 2, which is minus 2j. And at k equals to minus 1, what do I have as the coefficient? A suffix minus 1, which is minus j, right? So this is minus j. At k equals to 0, of course, since it is of the form j times k, so at k equals to 0, we get 0. So a0 would be 0, a0 is 0, and similarly I can find a1, which is j, a2, which is 2j. So you see that I mean these coefficients have kind of an odd symmetrical behavior because my AKs are my yeah, they're following an odd symmetry clearly, because a minus 1 is simply a minus of a1, also a minus 2 is minus of a2, and at a0 I have 0. But anyways, now we have the knowledge of these coefficients, so we can find the exponential series representation of x of k like this. jk omega naught t. We also know omega naught, and we are not really interested in this entire range from minus infinity to infinity, because only the coefficients for minus 2 to plus 2 will contribute to the summation, because the rest of the coefficients are 0. So this is ak e power um, just a second. Okay, yeah, e power jk omega naught t. So omega naught was pi by 2, j k pi by 2 into t, right? Omega naught was pi by 2. Yeah, fine. So what do we have? Okay, let me go to the next page. We will have 5 terms, right? So this is, so your x of t is a minus 2, corresponding to k equals to minus 2. I'll have a minus 2 times e power uh, minus j pi t. Yeah, minus j pi t, because for this exponential term here I'm putting k equals to minus 2, so I'll have e power minus j pi t plus a minus 1 into e power, again what do I have, um, minus j pi by 2 into t. Okay, yeah, and for a0 I'll just have a0, because e power jk term, that term will be equal to 1, because I'm putting k equals to 0. And for k equals to 1 I'll have a1 times e power j pi by 2 into t, and for a k equals to 2 I'll have a2 into e power j pi t. Yes. Okay, now let's just find this, compute this. A minus 2, what was a minus 2? Is minus 2j, so minus 2j into e power minus j pi t plus a minus 1, what was a minus 1? Minus j, so this is minus j into e power minus j pi by 2 into t plus a naught, what was a naught? A naught was 0, so nothing here, plus a1, a1 is plus j, so j into e power j pi by 2 into t plus a2 is 2j, so 2j into e power j pi t. Okay, now I can take some terms common together. So for example, this exponential terms, right? So yeah, I can club these 2j coefficients together, and for one such term I'll have okay, if I take 2j common from these two terms, let's say, okay, these two terms, what do I have? 2j into e power j pi t minus e power minus j pi t. And similarly, now if I take j common from these two terms, what do I have? Plus j into e power j pi by 2 t minus e power minus j pi by 2 into t. Just a second. right? So now remember that we know that we can actually express this exponential terms here as sinusoids, because we know that the relation e power j theta minus e power minus j theta by 2j is equals to sine theta. Okay, we know this, and we can replace this term, the difference of these complex exponentials inside the brackets, as sine functions. So what I'll do is I'll use this relation, and so this term will become, my theta is pi into t here, so it will become 2j sine pi t. And for the second term we'll have again 2j sine pi by 2t. So overall what do I have? Okay, so 2j into 2j will give you 4j squared, which is minus 4. So minus 4 sine pi t plus 2j squared, that is minus 2 sine pi by 2t. So I'll take this minus sign outside, and I have 4 sine pi t plus 2 sine pi by 2t. Note that here I can't simply say that sine pi t is equal to 0. Okay, because t is not an integer here. T is my continuous time variable, which can take any real value. Okay, it can be fraction as well. So but if it was some sine of pi k, where k is an integer, then it is always 0. Okay, right. Okay, so this is my signal. Okay, of course it is periodic also. Great. In fact, you can verify from here also. So initially we knew that from the given data in the question, x of t plus 4 is equals to x of t. So the period is, fundamental period is 4. So we ended up with this function, right? So now we can actually verify that as well. Take for example the first term here. What is the LCM of this? Sorry, what is the period of this? This one has a period of, let's say, let me call it as t1, which is 2 pi by pi, that is 2. What is the period for this one? Let's say t2, which is 2 pi by 2, which is 4. Now overall time period is LCM of my t1 and t2, which is LCM of 2 and 4, which is 4, which is true. That's another way of verifying. So okay. Okay, so now let us move to the last problem. So it will have some subparts. Okay, so this is the fourth question. Again, we'll explore the different properties of Fourier series, okay, through this example. Okay, what we are given is, let x of t plus capital T is equals to x of t. So which tells you that x of t is a signal, it's a periodic signal with fundamental period equals to capital T. And it has Fourier series, exponential Fourier series coefficients denoted by ak. Now you're asked to derive the Fourier series coefficients of the following signals in terms of these ak. Okay, you know ak are your exponential Fourier series coefficients for your original signal x of t. Now in these problems, you are given some modified versions of the original signal. For example, in part A, you are given a time shifted version of the original signal. So you are given x of t minus t naught, and you have to find its corresponding Fourier series coefficient and relate it with ak in terms of ak. Okay, and likewise you have other parts. For example, in part B, you are given a time reversed version of your original signal. You are given x of minus t. So what are the Fourier series coefficients of x of minus t in terms of your original Fourier series coefficients ak, and so on. Okay, so let's do it part by part. Now question number 4, x of t plus capital T equals to x of t, and I know x of t has Fourier series coefficients ak. So this fs is an acronym for Fourier series. This is my Fourier series coefficient. Now in part A, I have been given a time shifted version of my original signal x of t. So I am time shifting by an amount t naught. Okay, and I have to find its Fourier series coefficient in terms of my original Fourier series coefficient of x of t. So in terms of ak, I have to find the modified Fourier series coefficient. So first of all, let me express x of t in the exponential Fourier series representation, because this ak is the exponential Fourier series coefficient. It is given in the question. This ak are your exponential Fourier series coefficient. See, exponential Fourier series coefficients ak. Okay. So I have to represent x of t as in the exponential Fourier series form, so which is given by summation k running from minus infinity to infinity ak e power jk omega naught t. This I know. Fine. Now my modified signal is x of t minus t naught. So this function will have a corresponding exponential Fourier series representation given by. So basically what you need to do is, on the RHS, replace t by t minus t naught. That's it. So this is ak e power j k omega naught into t minus t naught. Because now the argument inside this x is t minus t naught, and it's not simply just t. So what do we have? This is summation k running from minus infinity to infinity ak e power jk omega naught t, and also I'll have another factor e power minus jk omega naught into t naught. Okay. Okay. Now I am slightly rearranging this. So I am bringing this last term here, e power minus jk omega naught t naught, in front next to ak, like this. So treat these two as together, and I'll be left with times e power jk omega naught t. So now just compare these two. You can actually denote this whole thing inside the bracket as some bk, let's say. So this is of the form k running from minus infinity to infinity bk into e power jk omega naught t. So it is the Fourier series, exponential Fourier series representation of x of t minus t naught. But now my Fourier series coefficients are bk's, okay, and where my bk is this ak times e power minus jk omega naught t naught, okay. So this is how my new Fourier series coefficients of my modified signal are related with the Fourier series coefficients of my original signal. Okay. So the answer is this ak into e power minus jk omega naught t naught. This is my Fourier series coefficient of x of t minus t naught. See, this is the same thing that happens in normal Fourier transform as well. If we shift the signal, we it results in an exponential, complex exponential multiplication to our Fourier transform, right? Remember that if I have x of t and let's say its Fourier transform, continuous time Fourier transform is some capital X of j omega, then if I have x of t minus t naught, the shifted signal, its Fourier transform will be e power minus j omega t naught into capital X of j omega. So this exponential terms comes into the picture. So similar thing is also happening here as well in the Fourier series representation, in the Fourier series coefficients. So this is one property, okay. What happens to your Fourier series coefficient if you shift your signal in the time domain? Great. Now so yeah, you can actually so basically what we concluded is that if x of t has Fourier series coefficient ak, then x of t minus t naught has Fourier series coefficient ak into e power minus jk omega naught t naught, right? This is one property. Now moving to the part b. In part b we have the time reversed form of your original signal, which is x of minus t. So what is x of minus t? Let's say x of t is something like this. Okay, since we are dealing with periodic signals, let me let's say it has something like this, and so on. If x of t has this kind of a nature, then what is my x of minus t? It is the time reversed signal. So what you do is you take you actually flip the signal, or in other words you reflect the signal about the vertical axis basically, okay. So you treat this vertical axis as a mirror and you take its mirror image. You reflect the entire signal about the vertical axis. So how does it look like? So let's say this is the point t equals to 0. So on doing that, you will have something like this. So 0. Okay. Okay. So this is just to give you a feel of the time reversal operation. But yeah, what we need to find here is what is my Fourier series coefficient of x of minus t. So, and I have to represent that in terms of ak. So x of t again, I know that its exponential Fourier series representation is this. Okay. Right. Now, what about x of minus t? So, if x of t is this, then what is x of minus t? You replace t by minus t. So, this is ak e power jk omega naught. So, this negative sign comes here, right? Okay. Okay, now what you do in exponential Fourier series representation, we need to ensure that these phasor terms, they have e to the power j k omega naught t term. There should not be any negative sign in the exponent. So to take care of that, what we can do is we can actually let we can substitute m some other variable as minus k. So accordingly we have to adjust the upper and lower limits. So here our previous variable, which was k, was running from minus infinity to infinity, and it's an integer. Our new variable that we are introducing is m, which is the negative of k. So that runs from plus infinity to minus infinity. But again, I mean, the range of values are the same thing. I mean, it does not matter if you are having the values minus 2, minus 1, 0, 1, and till 2, or till, I mean, from minus infinity to all the way till plus infinity. If you flip the sign of each of these numbers, you still have the same range actually. Okay. So this will also give you, plus 2, plus 1, 0, minus 1, minus 2, same thing. It's just that in one case you are going from minus infinity to infinity, in the other case you are going from infinity to minus infinity. That's it. So yeah, this is the thing. And now how can we rewrite this? We can rewrite this as x of minus t equals to summation. Now I'll replace k by m, and m is running from plus infinity to minus infinity, and I'll replace k by minus m. So this becomes a minus m e power. Again I'll replace k by minus m, so that will give me e power j m omega naught t. Correct? Okay. Now I can also interchange the upper and lower limits here in the summation, because why? I mean, adding terms from positive infinity to negative infinity is the same as adding terms from negative infinity to positive infinity. It does not matter. So let's say if you have this set minus 2, minus 1, 0, 1, 2 like this, it does not matter if you are adding from left to right or from right to left. Correct? So at the end of the day, you are computing the sum of all the Fourier series coefficients. It does not matter from which direction you are taking the summation. So this is same as m running from minus infinity to infinity, a minus m e power j m omega naught t, right? So yeah. Now what I can do again is simply replace this variable m by k. That's just a change of variable, which I can do, right? Does not really matter. So I'll replace m by k again. A minus k e power j k omega naught t. Does not change my result. So changing in this step, what I am doing is changing variable name, basically changing variable from m to k. Okay, now see, now what is the thing? So now this ak here, this is my Fourier series coefficient, because I am exactly in my exponential Fourier series form. So x of minus t has Fourier series coefficient a minus k. Okay, so the property that you verified here is that if x of t has Fourier series coefficient ak, then x of minus t, which is the time reversed version of x of t, will have Fourier series coefficient a minus k. So let me actually highlight them inside boxes, okay, so that the key takeaway is, you know, enclosed in a box. So similarly for the previous part also I am capturing this key result in a box. Okay, what happened in the case of time shifting. All right, now coming to our third part, part C, which is x star of t. What does x star of t represent? It is the complex conjugation of x of t. It's the same thing as you do for a complex number. It's just the complex conjugate of a complex number, right? For example, remember, if you have a complex number z as x plus iy, where x is your real part and y is your imaginary part, then z star, which is the complex conjugate of z, sometimes it is also denoted by a bar on top of z. So that complex conjugate is given by x minus iy. That's it. So this is known to you, right, from high school mathematics. So that's simply the definition of complex conjugation. And now what do we need to do here is, if we have x star of t, what is its Fourier series coefficient? Exponential Fourier series coefficient. So again, let's do it. So x of t we know as this representation in exponential form, right? Now what about x star of t? So I am taking the conjugate, complex conjugate of x of t. So I have to take the complex conjugate of this whole thing, right? My entire function, e power jk omega naught t, this whole conjugate, right? Hmm. Okay, now what I can do is, of course I can bring the summation outside. It's by virtue of linearity, I can simply take the summation outside. And other than that, I have product of two complex numbers. Why complex numbers? Because of course e power jk omega naught t is a complex exponential, it's a complex number, and ak, which is our Fourier series coefficient, can be in general a complex quantity. So that's also in general a complex number. So I have product of two complex numbers and I'm taking the whole conjugate of that. So that will give me the product of their individual complex conjugates, right? So basically what I am saying is that this will equal to summation. I can bring the summation outside by linearity, and I'll have AK star, okay, the complex conjugate of my AK times e power jk omega naught t, that also complex conjugate. And how I am writing this? Because I know if I have some z1 and z2 complex numbers and I have to take the complex conjugate of their product, then it is simply z1 star times z2 star. For all z1 z2 belongs to complex number set. Okay. So what are we getting here? K running from minus infinity to infinity, a k star e power minus jk omega naught t, because the complex conjugate of e power jk omega naught t is simply e power minus jk omega naught t. Okay. Again, now what are we done here? Not really, because here in the exponential term we have a negative sign in the exponent, but we need to ensure that there is no such negative term. So again we have to substitute introduce some new variable, right? Some m equals to minus k. Again the same thing we have to do. So let me go to the next page. So let m equals to minus k. So again I have to modify my limits. Like last time we saw, it doesn't really make a big difference. So since k runs from minus infinity to infinity, my m will run from plus infinity to minus infinity. That's fine. And my function here, sorry, so yeah, so I wanted to actually, yeah, I don't know why this is happening. Okay, so yeah. So now what happens to my x star of t? This is simply summation. Now my new variable is small m, which runs from plus infinity to minus infinity, and I'll replace k by minus m here, a minus m star times e power j m omega naught t. Okay, now one more thing what we can do is we can simply interchange the upper and lower limits, because summing numbers from negative side to positive side is the same as summing numbers from positive side to negative side. It's the same thing. Ultimately the result of the summation is the same, so it doesn't matter from which direction you take the sum. So this can be replaced by m running from minus infinity to infinity, a minus m star e power j m omega naught t, and again Like last time, we will just do a change of variable. So this is, I'll replace m by k again. Okay. So what do I have? This term, a minus k star. This is my Fourier series coefficient. This is my Fourier series coefficient of x star of t. Okay. So the takeaway is that if x of t has Fourier series coefficient ak in exponential, I mean exponential Fourier series coefficient ak, then x star of t, which is the complex conjugate of x of t, will have Fourier series coefficient a star minus k. All right. So now coming to the part D. Okay, and part D is straightforward now because part B is just a slight extension of part A. Because you see, in part A we already found the Fourier series coefficient for x of t minus t naught, and in part D we are being asked as just a linear combination of such shifted signals. So what we have is x of t minus t naught plus x of t plus t naught. So you can now use linearity and come up with your new Fourier series exponent, Fourier series coefficient. So that's exactly what we are going to do. So you need to find the Fourier series coefficient for this term here. Okay. So from 4a, we already have that x of t minus t naught had a Fourier series, I mean, had an exponential Fourier series coefficient given by ak times e power minus jk omega naught t naught, right? So it's e power minus jk omega naught t naught into ak. So now what will be the corresponding Fourier series coefficient for x of t plus t naught? Simply replace t naught by, I mean, yeah, you just add a negative sign here, right? So you replace t naught by minus t naught. Okay. So what do we have here? It is simply e power jk omega naught t naught into ak. Now all we need to do is just add them together and use linearity to find the overall Fourier series coefficient. So therefore x of t minus t naught plus x of t plus t naught has a Fourier series coefficient which is given by the sum of these two individual Fourier series coefficient. So this is e power minus jk omega naught t naught into ak plus e power jk omega naught t naught into ak, right? So how did I write this? This is simply using linearity. And now can I simplify this further? Let's see. So this whole term here, I can rewrite this as, I can actually take ak common. So this is ak times e power jk omega naught t naught plus e power minus jk omega naught t naught. And again, this is a familiar expression, because now again we can express this as a cos function, because we know that e power j theta plus e power minus j theta by 2 is equal to cos theta. So here we can actually replace the sum of exponential terms as twice into cos terms, so which will give us 2ak cos k omega naught t naught, right? So this is my Fourier series coefficient. And again, I'll summarize the result in a box. If x of t has Fourier series coefficient denoted by ak, then x of t minus t naught plus x of t plus t naught has a Fourier series coefficient given by 2ak cos k omega naught t naught. This is nothing special because this is directly coming from the time shifting property and of course linearity. Okay. Now moving to the last part, the last problem, which is 4 part E. So this is odd function. This is the odd part of x of t. Okay. This denotes the odd part of the signal x of t. Okay. So what we need to find is the Fourier series coefficient of the odd part of x of t. And we know the odd part of a signal, the expression, the odd part of a signal. So this is, let me write it anyways, odd part of x of t. So odd part of x of t is given by x of t minus x of minus t by 2. Had it been an even part of x of t, then it would have been x of t plus x of minus t by 2. Okay, so we have looked at these things several times before. In case you are not familiar, I suggest you go back and uh, brush up on those things. So this is the odd part representation of a signal. And now what do we know? We already know that okay, x of t has Fourier series coefficient ak, right? Okay, now in the odd part of x of t, we have two terms, right? A linear combination of two terms. Half into x of t, which is our original signal, and we know that its Fourier series coefficient is ak, so that's fine, minus half into x of minus t, so that's the time reversed signal. And from our previous parts, actually I think in 4b, yeah, in 4b we found the Fourier series coefficient of x of minus t, which was simply a minus k. See, so we also know the Fourier series coefficient of x of minus t. So together we can combine them using linearity and find the Fourier series coefficient of the odd part of x of t. So what do we have? So from the result of 4b, we have x of minus t has a Fourier series coefficient a minus k. Therefore, x of t minus x of minus t divided by 2, which is the odd part of x of t, will have a Fourier series coefficient ak minus a minus k divided by 2. And again, what I am using here is simple linearity. So my conclusion is that if x of t has an exponential Fourier series coefficient ak, then my odd part of x of t will have Fourier series coefficient ak minus a minus k divided by 2. Okay, so we have covered all the questions for today's session, and yeah, that should help you with the understanding of, first of all, the Fourier series, the concept of Fourier series. How do we find the Fourier series coefficients? By taking Fourier transform of periodic signals. And we have also revisited a bit of our high school calculus, such as the integration by parts and so on, in solving these integrals. And uh, we also we also we also studied these signals graphically as well, besides their mathematical representation, and we verified our answers uh, in multiple directions. Say for example, when we were computing the DC component, so this Fourier series coefficient corresponding to index 0, this a naught for example, it actually represents your DC component. As we saw, right, it's simply the area under the signal, the average value of the signal over one time period. So we calculated the area also. For example, here we calculated the area of the shaded region and then divided it by the fundamental period and ended up with the same value. And using the mathematical approach also, we used the formula and found that we are getting the same expression for a naught. And then of course we found the general expression for the Fourier series coefficient for k not equals to 0 as well. And yeah, and once we have the knowledge of the Fourier series coefficient, we have the complete knowledge of the signal x of t. And in the fourth problem, we have looked at almost all the major properties of the Fourier series coefficient. So we studied time shifting, we studied time reversal, we looked at complex conjugation, and then linearity, of course, and of course the odd part of x of t. And similarly, you can do the same thing for even part of x of t and other things such as real part of x of t and so on. So let me stop at this point, and hopefully it was a fruitful session, and we'll meet again on next Monday 6 p.m. So thank you.